Hi, so welcome to another exciting installment of Advanced Computer Architecture. And what we're going to do today is introduce the topic of pipelining. So I imagine many of you have encountered this before, and what we're going to do is look at the fundamental issues, the issues of hazards and stalls and forwarding, how to handle multiple functional units in a pipelined processor, how to schedule instructions to avoid stalls in a processor, all of those things. So this is a second or third level computer architecture course, and my aim is to get you basically from what a first year Department of Computing student will have learned, together perhaps with some of the compiler issues, all the way up to understanding the latest commercially available processors. And it's my job to achieve that stretch to the point where we'll be able to study the latest processors in detail, to argue and reason about how they're designed, why they're designed that way, how they could have been designed differently, what pressures and constraints and tensions emerge during that design process, and how we might expect future processors to be architected. You will need to do some homework. You will need to look not only at the textbook, but in fact I think you would benefit from studying further beyond that too. You will find many similar courses to this one with materials on the web, and of course there are other sources too. We're really keen to help you succeed as a student and get what you want from this course. I'm here because I actually want you to learn things. We will try very hard to support you both live in interactive sessions through pre-recorded material like this, and through online forums like Piazza. So here's the starting point. Imagine a simple processor instruction set. So we're going to use, for the sake of argument, the MIPS instruction set here. It's a reduced instruction set design. What that basically means is that every instruction is exactly the same width. It's 32 bits wide. That makes it easy to decode and so on. So what we see in the binary encoding of such instructions is that of the instructions for this processor are that there's an opcode that occupies these top bits instruction encoding. There are some register specifier fields that also occupy fixed positions in the instruction. The point of that is that you can start accessing the registers needed for a particular instruction before you've even finished decoding it, before you even know what kind of instruction it is. So some instructions have two source registers and a destination register, something like an add instruction. Some instructions have a source register, a destination register, and an immediate operand. So if you want to add 123 to a particular register, you can do it in one instruction, and you specify the constant that you're adding here. Conditional branches, registers specified here, and if they're equal or less than or something, then you want to branch to some. One difficulty in the design of a RISC instruction set is that the target of that branch address needs to fit into the instruction encoding. So the immediate operand here is not an absolute address, because that would require more bits. It's a relative address relative to the current program counter's value. And what we need to do is to add the current program counter to this immediate operand to get the actual branch destination. And of course it's possible that you actually want to conditionally branch to somewhere beyond the range represented by this immediate operand. There are only 16 bits here. We're going to scale them up because we know that the address will be word aligned, so we can multiply this number by 4. But it's still a bounded extent, and for large software you may need to do something else. We also have an unconditional branch, which can branch to any address in the full address space for this 32-bit machine. So if we look at some example instructions encoded this way, here's an add instruction And what it does is it updates the destination register with the sum of the two operands. Here's a load instruction, and this is why I'm showing you this. This load instruction uses this format because what it's going to do is specify a source register, a destination register for the result to be loaded to, a source register which is to be added to this immediate constant. So you can imagine that this is useful for things like accessing the fields of a struct or something like that. So if you have the fields of an object, the members of an object, or the fields of a struct in C, then the field offset could be this constant here, represented in this immediate field. And we can access the fields of an object using a pointer to the base of the object in one instruction. So that's quite a handy thing to be able to do. What it means is that we need to do some arithmetic for every load instruction. Store instructions, basically exactly the same. We use the same format for an add immediate operand, as I was saying. One little subtlety here is, suppose that this constant here, this immediate operand, is a negative number. What we've got is a 16-bit negative number, and what we need to do is use it as if it were a 32-bit negative number, so we need to sign extend it. Essentially, if it's a negative number, then we need to fill in the ones for the remaining bits, remaining high-order bits. The conditional branch is the relative addressing operation that I mentioned. Actually, we're going to update the program counter to PC+4 with every instruction, of course. In the conditional branch, we see that we're going to update with PC+4 and then add this offset multiplied by 4. Each instruction is 4 bytes, and we want to use the bits more efficiently. Questions you might ask about this are, so how many registers can we have in this machine? Well, it's determined by the width of the register specifier fields. And in the MIPS instruction set, that's 5 bits, 2 to the 5 is 32, and we can have up to 32 registers in the machine. If you wanted more, then you would need a instruction encoding that devotes more bits to register accesses. And that would mean that you have fewer bits for immediate operands, for branch targets, and so on. So there's a trade there between the largest signed immediate operand that can be specified and the number of registers that you need. What range of addresses can you conditionally branch to? Well, it's basically also determined by the size of that immediate operand, though we will scale this value by 4, as I mentioned before. So where we're going with this is to build machines to execute this instruction set. And what I'm suggesting here is an outline for a machine to do it. This is the fetch execute machine. What does it do? Well, it fetches an instruction from memory, and we might as well at that point also increment the program count. The register is specified in the instruction right away. So we're going to grab the immediate operand from the instruction encoding. We're going to grab the register specifiers and look them up in the register file. Now we can actually do the operation specified in the computation. So if it's an arithmetic operation, that's where it's going to happen here. And then if it's a branch, then we're going to use that result to update the program counter. If it's a store, we're going to send that operand to memory. If it's a load, we're going to collect that operand from memory. And then the final step is where we actually update the target registers. Why am I going through this in all so much detail? Well, because we're going to design a machine to do it in hardware. And here's my attempt to show you such a thing. So along the bottom here, we have those block that I mentioned to you before, and you might have thought they were a bit stylized. The reason was because we're going to do this. In this stage of the design, we're going to use the current program counter as an address into memory, and we're going to also increment it by 4. In the next stage, we can pass the register operands from the instructions that we've just fetched to the register file to look up those values in registers. We can also collect from the instruction encoding, we can collect the immediate operand, sign extend it, and pass it forward. In this stage, we're going to select where the operands for the arithmetic operations are actually going to come from. So if it's a conditional branch, then the operand for the arithmetic operation actually comes from here, right? If it's a register add instruction, then both operands are going to come from here. If it's a immediate add instruction, then one operand comes from a register and the other comes from the sign extended immediate operand. Now, for a load instruction, the result of that arithmetic operation, like R2 plus 100, is going to be used as an address to fetch data from memory. And so in this phase of the machine, we actually access the memory, collect the data into a memory access register, and then the final step is where we write back. We write back any updated registers from the execution of this instruction. So I've introduced this architecture as a machine for executing the instructions in our MIPS instruction set as a sequence of phases. And the reason, of course, is because we're going to pipeline this machine. That's the subject of this lecture. And it's clear that I've structured this for you as a sequence of phases. What we're going to do to pipeline it is introduce buffer registers between the pipeline stages, like so. So in the pipelined design, we can fetch an instruction, stash the instruction that we fetched in a pipeline buffer latch here, and then in the very next instruction cycle, we can fetch the next instruction whilst that instruction is passed to this stage of the pipeline. And then the register operands that we fetched from the register file can be stashed in these latches here. So in the next instruction, next clock cycle, we can be doing this pipeline stage can be operating on the next instruction, and so on. And an instruction that's fetched here progressively moves down the pipeline with each successive clock tick. Of course, what we should do is distinguish all of that from what happens without pipelining. Without pipelining, well, I haven't really spelled out exactly how this would work, but presumably this would be a combinational logic structure which would execute one instruction per cycle, and the depth of this design, the number of gates along the longest path through this design, would determine the clock cycle time, the amount of time it takes to complete all that logic computation, and therefore determines the clock rate at which the processor can run. Because that pathway is very long, such a non-pipelined processor is going to run very slowly. What we can do with pipelining is run at a far higher clock rate, because the clock rate is determined by the rate at which each of these individual steps can be done. So the clock rate is determined by the slowest of the 5 pipeline stages, whichever it is, and the logic depth of each of these pipeline stages is controlled in order to enable us to run at the highest possible clock rate. Of course, what I didn't tell you when I first introduced this is that there's a need for some kind of control in this machine. So where does that kick in? Well, it's these multiplexers, for example, and this arithmetic unit here needs to be told whether it's supposed to do an add or a subtract or what. The memory here needs to be told whether it's doing a read or a write, and this multiplexer here needs to be controlled, and so does this one. So for example, if we decode the instruction and we discover that it's a conditional jump, well, what happens in a conditional jump is that we're supposed to add the current program counter, which is here, PC plus 4 coming in here. We're supposed to add that to the immediate operand, remember? So we need to configure these two multiplexers. This one to take this operand, this one to take this operand, and the ALU to do an add. to compute the branch target address. We also need to configure this multiplexer to pick that value rather than the value coming from the memory. For a register-register add operation, this multiplexer would pick the first operand from here, and this multiplexer would pick the second operand from here. We'd configure the ALU to do an add. We'd configure this multiplexer to pick the value coming from the arithmetic unit here. So we can visualize what's going on in such an architecture by thinking about the fate of a sequence of instructions over time. So imagine a sequence of 5 instructions over a sequence of clock cycles, and imagine for a moment that the processor is initially idle. So in the very first cycle, all of the pipeline stages in the machine are idle, except for this one, which is fetching the current instruction. In the next clock cycle, the instruction that we fetched here is passed into the register decode and into the decode and register fetch phase, but the instruction fetch element is no longer being used by instruction 1. In fact, it's available to be used in cycle 2 to fetch instruction 2. And in the next cycle, the register operands that we fetched can be passed into the arithmetic stage, the execute stage, and so on. So we get this successive overlap of this sequence of 5 instructions, like so. So in each successive clock cycle, more and more of the stages of the pipeline are busy until eventually, after 5 cycles, all of the pipeline stages are usefully employed. So here we have the fetch for instruction 5 being done in parallel with this stage, the decode and register access stage for instruction 4, in parallel with instruction 3's execute stage, with instructions 2's memory stage, and instruction 1's write-back stage. And usually, in an ideal world, this pipelining would then continue indefinitely, fully occupied. Eventually, of course, we're going to have a drain phase to the pipeline, where we find that not all of our pipeline stages are usefully occupied as we finally drain the last value out of the pipeline. So, what do we learn about pipelining from thinking about this simple processor? Well, firstly, we should realize that pipelining doesn't help make individual instructions complete more quickly. It doesn't help the latency of a single instruction. The latency is the time that it takes, that you have to wait from starting the instruction to it finally finishing. What it does instead is helps with the throughput of the entire workload. So we can start an instruction every single clock cycle. We can finish an instruction every single clock cycle, but no one instruction completes any quicker. But we can run at a very high clock rate because we've reduced the logic depth of each of these pipeline stages. The pipeline rate is limited by the slowest pipeline stage, and you might wonder which pipeline stage is going to be the slowest. In fact, I chose to decompose this instruction execution pipeline into 5 stages. I could have chosen 2 or 3, perhaps 4, and you'll see later in the course processors where many more pipeline stages are used. Even for simple instruction sets like this one, we can extend to 8 or more. For more complex architectures, we'll find pipelines that are really deep, like 31 stages in the Pentium 4. Another nice thing about this is that pipelining kind of comes for free. We didn't add any new units, but we did successfully use them all in parallel with each other. The price we had to pay is that we had to add these latches here. And that does cost a little bit. It costs a little bit in transistor count and energy and so on. So when you think about pipelining, you might think, well, more pipelining would be even better. But eventually that benefit starts to run out. If you over-pipelined this architecture, then the clock rate would start to be dominated by the time the signals spent in these latches, in these red latches here. So I've suggested to you that pipelining is a fantastic idea, and it is a fantastic idea. It's an essential idea, but it comes with some big problems, and this is really why we're here in today's lecture, because we want to look at hazards. Hazards like the hardware, if you've got a particular unit in the hardware, it can't be used by two different pipeline stages in the same clock cycle. I'll show you an example of that in just a moment. A more classic and more obvious hazard is a data hazard, where an instruction depends upon the results of a previous instruction that hasn't been completed yet. And I'll show you examples of where that causes a really bad problem, where we simply fail to successfully pipeline, where we get a pipeline bubble or a pipeline stall. And I'll also show you some examples of data hazards where we can overcome that with a trick called forwarding. The third kind is the really awful kind, actually. I kind of assumed when I showed you this picture that as we fetch an instruction here, we know what instruction to fetch in the next clock cycle, even though we haven't decoded the previous instruction. Well, what if that previous instruction was a branch? In that case, we actually should be fetching some other instruction. That's a control hazard, and we'll come to that in a minute too. So let's look at the structural hazards that I promised you. And what I want to do is show you a real issue from a real processor. I don't know if any of you have ever used the Sony PlayStation 3. Things have moved on since then. It goes back a ways. It was an unusual and interesting project because it was based upon a highly parallel multi-core processor chip developed in a consortium between IBM, Sony and Toshiba in sort of mid-2000s. And Sony were interested in it from a gaming point of view. The other partners had other interests. The processor, the cell processor, the cell broadband processor it was called at the time, consisted of two parts. It consisted of a rather conventional PowerPC based processor to run the Linux operating system, and then it had 16 parallel accelerator units for making stuff go faster. And these were extremely fast but extremely simple processors. And one of the reasons they were particularly simple is they had no caches at all. They just had a block of SRAM for storing both instructions and data. And that's the problem. That's the structural hazard that this processor suffered from. So if we imagine here, we execute a load instruction. And so we fetch it, we decode it. And at this stage in the pipeline, a load instruction is going to need to use that memory. And that's great. But here down the way, 3-4 cycles later, of course we're going to want to fetch instruction 3 from the instruction from the same memory. Remember, in the cell broadband engine's accelerator processor, the SPE, there is only one memory, and so there's a structural hazard caused by that simultaneous access. Basically, it looks like every time you do a load instruction, you cause an instruction fetch to stall. What happens when it stalls? Well, basically that means that in this clock cycle we can't fetch that instruction because the memory is busy, and instead we're going to delay and fetch it in the next instruction, in the next clock cycle. What that does is it causes what is often called a pipeline bubble. It's an unused instruction issue opportunity, because once we fail to use the instruction fetch stage here, then the subsequent pipeline stages are going to be idle in a sequence as the missed instruction propagates through the pipeline, as the instruction bubble propagates through the pipeline. What the IBM architects actually did, what the cell processor architects actually did, was they had a prefetch buffer. So when you do fetch an instruction from the memory, you fetch a block of instructions and you fill an instruction queue. And so accesses to the memory for fetching instructions only happen when the queue is empty. So it doesn't happen every single time there's a load instruction. It happens when there's a load instruction and the instruction fetch queue happens to be empty at that time. And actually what they did was in the compiler for this machine, they count the instructions, they calculate at compile time what the state of the instruction queue will be, and they reschedule the instructions to avoid these conflicts. So that's a structural hazard. Let's look at a data hazard. And this is kind of the fundamental one. This is the one that you kind of can't escape. So let's think about this instruction sequence. So I've constructed a sequence here where register R1 is computed in this instruction as an add, and then it's used in all of these subsequent instructions. It doesn't matter what particular operations they are. The important thing is that they're all used. So what we said was that we do an add, we fetch R2 and R3 here, we do the add here, we produce a result for R1, but it doesn't get written to the register R1 until the write back stage of the pipeline. And that's a bit of a problem because the next instruction might, as this one does, try and use R1. And R1 has not yet been written to the register file. So in this clock cycle, R1 still holds the wrong, old value that it had before. It seems like we need some kind of magic time travel to pass the value backwards in time here. And obviously that's not going to be possible. In fact, it's kind of worse than that because this problem affects not just this instruction, but the next one as well. Things only start to look up here and potentially here. So in this last case, the situation is quite clean and simple. We compute the value, we assign it into the register, and then in the next cycle, we can read it from the register and get the right value for R1. In this case, well, this depends a little bit on exactly how you've designed your architecture, but a common trick is actually that the write back updates the register in the first half of the clock cycle, and the register read operation fetches the register value in the second half of the clock cycle, so that this instruction does in fact collect the correct value of R1. But what are we going to do about these two? So you will have noticed, I hope you might have thought about this already. Let's see. Here, what I suggested in the previous slide is we have to wait for the value to be written to the register before we can use it. But that's kind of frustrating because the result of that add instruction is computed at this point. And so we could, you might think, pick it up and pass it direct to where it is needed. As essentially as we take the output of the arithmetic unit from the add instruction, and in the very next clock cycle, it becomes the input for the same arithmetic unit for the subtract instruction. Okay, so that idea is called forwarding, and it's a big one that we'll see a lot more in a little while. So that solves the problem of getting this value to this instruction, and in fact the same idea can be used to get the value to this instruction too. a little subtlety, we need to delay that value by 1 clock cycle before we forward it. So that's a forwarding in principle. Let's look at how we have to modify our hardware to do this. So here's the relevant parts of our pipeline. And what we're going to do is add blue wires. So the blue wires are the forwarding paths. What we're going to have to do is to expand the input multiplexer for the arithmetic unit. And we're going to have to expand it to select where the operand is supposed to come from. So the normal case is it comes on a black wire, for example, from a register. But if the value that you want is actually going to be forwarded because it's not yet been written back to the register, then we need to choose one of the blue wires. Either this one, which is where we pass the result of the arithmetic unit in the previous cycle to the first operand of the arithmetic unit in the second cycle. This wire passes the value from here, from the cycle later, as I showed you in the previous slide. This is for forwarding the value to the next instruction but one. And this third wire takes the value from memory. So if this was a load instruction, then that's how we would get the value passed forwarded to the right place. Of course, what we haven't said is how you control these multiplexers. So when we talked about, if we just go back a few moments to the decode structure back in the pipeline architecture, where's it gone? Here. Whoops, I've gone badly wrong. So now with forwarding, what we have to do is extend the decode to control a bigger multiplexer at this point in order to select values from blue wires, which we're going to add for forwarding paths, as I showed you a moment ago. The question then is, how does the instruction decoder know what to do? Well, what it needs to do is to keep track of which registers are going to be updated by instructions which have not yet completed. And so at the point where an instruction is decoded, we know where the operands are going to come from. We know what other instructions are in flight and which registers they're going to write to. And so at decode time, we can choose a configuration for these multiplexers and pass it down the pipeline. So what we've hopefully got here is, so what we see in this diagram is an add instruction producing a value of R1, a subtract instruction producing a value of R4, and a add and instruction producing a value for R6. And we're passing a value from the output of the arithmetic unit here to the input of the arithmetic unit here, from the output of the arithmetic unit here to the input of the arithmetic unit here. In fact, the values are just going round and round through the arithmetic unit again and again to have this sequence of operations applied to them. The reason I showed you that is actually because what we want to do in this course is get more aggressive, or get more ambitious in our design. Imagine a fat processor that tries to execute multiple instructions per clock cycle, has multiple arithmetic units. Seems like a reasonable thing to do. In fact, many processors that you might buy do exactly that. So this forwarding is going to get a bit more complicated. What we're going to do is, what we're going to see is the dynamic construction of a data flow graph, of an allocation of this sequence of operations onto the arithmetic units over a sequence in time. So what we're doing there is resource allocation and scheduling, and configuring these forwarding paths accordingly. That we will see a lot more of later in this course. But forwarding isn't always going to fix it. Let's look at this. So this is a load instruction, produces R1, and these arithmetic instructions use the result of R1. Now the trouble with a load instruction is that in our pipeline design, the memory access stage comes late in the pipeline, after the arithmetic stage. You remember the reason for that was that this instruction set, a load instruction, involves taking this immediate operand and adding it to that register operand, and that's going to be done in the arithmetic unit before we compute the address for the RAM. So that's why the ALU comes before the data memory in our pipeline. What that means is that the value of R1 is obviously not in a register yet, but it's not even available until this point in time. And this next instruction might need it. Right? This subtract instruction needs the value from memory which is available at that point. And that arrow there is backwards in time. And there's nothing we can do. The value is not available from memory until this time. So we're going to get a stall. We're going to get a pipeline bubble due to that data hazard. This is actually a very common phenomenon in many processors, and it's called a load to use delay, or a load to use stall. Of course, what we need to do is to design the control logic for our pipeline, not only to configure forwarding, but also, in fact, to configure the machine to implement the resulting bubbles. So when we notice at decode time that this instruction needs R1 that isn't going to be available until this cycle, what we have to do is stall this cycle for one cycle, the pipeline for one cycle, in order to ensure that that value can be forwarded correctly. We need to implement the stall and the forwarding in order to get the value to the right place at the right time. So that's pretty bad. Load use stalls sounds like a really common thing that programmers might do. You load data from memory and immediately you want to be using it. What we could do is get the compiler to address this problem. So if you imagine a sequence of assignment statements like this, a simple compiler, like you might study in my in my compilers course, will compile each of these statements separately. So we'll have load B, load C, and then do the add, and then store the result. And then we'll have load E and load F, do the subtract, and store the result. And because that's a load followed by an add using that result, there's a stall at this point. So this sequence leads to two stalls. But a smarter compiler, beyond what you would learn in my second year compilers course, would look at this, it would know something about the stall behavior of the instructions, and it would reschedule these instructions. So you can move this load instruction, for example, a bit earlier to fill that stall. Stalls are missed instruction execution opportunities, and what we can do with instruction scheduling is move instructions around in order to use those instruction execution opportunities profitably. Similarly, we can take the stall here, the store instruction here, and put it in that stall slot, and so we complete the entire sequence in a couple fewer clock cycles. Obviously, more complex architectures benefit more from more sophisticated instruction scheduling. So we've done structural hazards, we've done data hazards, and I promised that we'd also talk about control hazards. So here we have a sequence with a conditional branch instruction. It's going to test whether R1 equals R3, and if so, it's going to add 36 to the current value of the program counter and jump to that address. The next instruction is the fall through case for this, right? So if we don't take this branch, what are we going to do? If we don't take this branch, we continue to execute, and we continue to execute this instruction. The question then is, of course, as I mentioned to you earlier, we fetch this branch instruction and we start decoding it at this point, but we want to be fetching this next instruction at the same time. But maybe that's a taken branch. Maybe that condition is going to turn out to be true, and we should in fact be fetching the instruction from PC plus 36 instead of this next instruction. In fact, when doing the right thing to fetch is? Well, that kind of depends on our pipeline design. One way to do this would be to do the comparison, the is R1 equal to R3. We could do it in the arithmetic unit, and we could and then we discover the branch outcome at this point. If we did that when we suffer a really bad stall, what we could do to try and make things a little bit better is to try and discover the branch outcome earlier. So what I suggested in the previous slide is that we don't do this branch comparison until the execute stage of the pipeline. And in fact, we also need to add the current program counter to 36 as well. So that involves two add operations. If we really only have one adder, then we're going to have to use this twice, and we're going to suffer a really long delay. What we can do is modify our pipeline. We can introduce a new adder here to add the current program counter to the immediate operand. And we can have a unit. We can also check the branch outcome. We can check whether the operands are equal or equal to 0 here. So we take the values from the register file and compare them to, we take the result from the register file, check if it's equal to 0, and if it is equal to 0, then we can use this computed next program counter value. So what we've done with this dark blue sequence here, is that dark blue units here, is we've moved all the logic associated with determining a branch outcome as early in the pipeline as possible. Of course, it's not quite early enough to avoid any stall at all. So if we go back to our pipeline here, what this does is it determines the branch outcome after we've decoded the instruction, fetched the register operands, determined whether the condition is satisfied, and computed the next program counter address in this cycle. It's too late, actually. We've already fetched the next instruction, but at least the resulting delay is much smaller than it would be. What we will see later in the course is how we can overcome even that delay. And what we'll see with branch prediction is how we can guess what the right instruction to fetch actually will be. Just to finish up, I thought I would show you an idea that actually overcomes all of the hazard problems that I've been telling you about. So that seems a bit surprising, but it's a very simple trick. Suppose that we take our processor and we execute two threads on it concurrently. So this is not like having two processors for two threads. This is about having one processor, and what we're going to do is execute instructions from the two threads in an odd even interleave. So in clock cycle 0, we're going to fetch from program counter 0, decode the instruction and access thread 0's registers, execute the instruction, and then write back to thread 0's registers. In the next clock cycle, we're going to fetch from program counter 1, access thread 1's registers, and write back eventually to thread 1's registers. And we're going to alternate odd even between PC0 and PC1. The point of this is that these two threads can't depend on each other via registers. They might have dependencies due to memory. One of them might write a value to memory and the other one might read it back. But what they cannot do is have a dependence where one of them writes to a register like R1 and the other uses R1, because they have completely disjoint register sets. So this trick, which goes by various names, and we'll cover this in much more detail later in the course, you can call it some kind of multi-threading, completely eliminates the data stalls, or at least it massively reduces the data stalls. If you really want to eliminate all of the data stalls, you might have to go beyond 2 threads and go up to perhaps 4 threads or something like that. What this might do is enable you to eliminate some of the complexity of your processor and perhaps even run it at a higher clock rate. So I mentioned the PlayStation 3, and earlier I talked about the PlayStation 3's SPE accelerator processors with their structural hazard. The main processor in the PlayStation 3 cell broadband engine is a PowerPC designed to run ordinary programs, including the operating system. And it has exactly it uses exactly this trick. And the reason why the IBM processor microarchitects chose this design was because they wanted to run this at a very high clock rate. And this trick enables them to eliminate some of the complexity in their pipeline. So how fast can we make this actually work? Well, typical 5-stage pipeline processors like the ones that I've been showing you, at a pinch, if you're aggressive about it, can run sort of 5 to 9 gigahertz. I'm sure people have managed to run processors at higher clock rates than that. What limits that clock rate is the critical path, as I mentioned. So the pipeline with the longest chain of combinational logic elements is going to be the slowest one that determines just how fast the clock rate can be. So you have a trade-off actually in designing a pipeline processor. You could either try to do more in each cycle with a deeper logic structure between each of those pipeline latches, or you can do more pipelining, which squeezes the amount that you can do in each pipeline stage, but run at a higher clock rate. And this is a classic and fundamental processor architecture design choice. So if you did want to run at about 3 gigahertz, the kind of performance, the kind of clock rate that your laptop processor might be running at, the clock period is 330 picoseconds. It's about 1/3 of a nanosecond. It's about the time light takes to go about 4 inches. It's about 10 gate delays in a CMOS design, CMOS process, fabrication process. So for example, if you go look at the article describing the cell broadband processor, they talk about how they address or what they did about this. They optimized for 11 gate delays. Actually, not all gates are exactly equivalent. Some gates are bigger and more complicated than others. The main factor that determines the time it takes for a signal to propagate through a gate is what the fan out is. How many other gates need to be driven by the output of this. So a unit of combinational logic circuit depth is fan out 4 logic gates. So the budget for the cell broadband engine was 11 fan out 4 logic gates per pipeline stage. One of the things to realize is that the pipeline latches, the red light pipeline latches between the pipeline stages, actually account for 3 to 5 of those already. So all your arithmetic calculations, all of the instruction decoding, the register accesses, and the memory stage, basically all of that has to be done in 5 to 8 gate delays. The maximum depth of your circuit can be only 5 to 8 gates. And the next step, the next chapter of this course is going to look at the memory system, because the critical part here, the thing that's really going to lengthen your clock cycle, is if the memory stage in your pipeline is too long. So, just to round off and summarize, this course is about fetch execute machines, where it's all about general purpose processors, universal computing machines, which are controlled by a program stored in memory. So the business of computer architecture is to basically fetch instructions, decode them, and execute them as fast as possible. And the fundamental idea here that we've talked about is that we can pipeline that process. Pipelining would be wonderful, it actually is wonderful, but what makes it complicated is the potential presence of various kinds of hazards. As I've shown you, hazards can be handled sometimes by forwarding the blue wires, but sometimes even forwarding won't help, and we need to introduce stalls or bubbles. Control hazards are even worse. They're just trouble. And there are various things we can do. The one I showed you is to try and move the branch, the decision about whether the branch is taken and to which destination, move all of that as early in the pipeline as possible. The trouble is that that doesn't move it quite early enough. And we're going to need some more tricks to deal with conditional branches. In fact, to deal with branches of any kind. And we'll cover that in a later chapter in the course. Finally, the pipeline design affects the maximum clock rate. And the performance of your computer is a combination of how many cycles does it take and how long those cycles are. And as a processor architect, you get to make choices that navigate those two constraints. Next up, a tutorial exercise on the connection between instruction sets and pipeline architecture, and then we'll dive into caches and the memory system.